Okay, let's begin. Hello, everyone, and welcome again to our webinar in differential geometry, AmSur. It is a pleasure to introduce today to Professor Francisco Vittone from Universidad Nacional de Rosario and CONICET from Argentina. And he will speak about nullity and symmetry in homogeneous spaces. Before Francisco begins, you can see all the relevant information about this webinar on the chat. If you want to join us in the mailing list or via WhatsApp, please look at this message. Okay, then, well, thank you, Francisco. You can go ahead, please.
Thank you. Okay, first of all, of course, thanks the organizers for the invitation to give this talk. I'm no longer seeing you because I am with the presentation in a full screen. So if there's a problem, please let me know if you don't listen or anything like that.
Okay.
Well, the talk is called Nullity and Symmetry in Homogeneous Spaces, and it's based on some recent works which I did with Carlos Olmos, which is here. So if you have any question, you can address to Carlos, and Antonio Di Scala of the Politecnico of Torino. And I wanted to tell very little about some recent research that we are doing with Silvia Reggiani and Brian Lupolini from Rosario. I will just mention it at the end of the talk. So the first part of the talk, which is introduction is I will speak about the tools that we use to solve these problems of studying these distributions. And I hope the tools will be useful to solve other problems. So I will try to go slowly in the first part. Many of you have already listened to these things, so I apologize. But well, at the end of the part, I will talk about the results we found. So when we speak about nullity distributions in general, one means a distribution which is given by the vectors of a tangent space of a manifold that annihilates some operator. In particular, if you have a Riemannian manifold and you take the Riemannian curvature tensor with respect to the Levi-Civita connection R, you can define at each point of M a subspace, which is called the nullity subspace of M at P, which is given by the vectors of the tangent space, which makes that the Riemannian curvature in any other direction is 0. So you have two different ways to define it due to the identity of the curvature tensor. You can put the vector in the first component and think that is the space of the tangent vectors that annihilate the operators Bx for each x of TPM, or just to think of the vectors that are annihilated by when you put any other two tangent vectors in the first two components of the Riemannian tensor, curvature tensor. So each subspace, each nullity subspace have a dimension which is called the index of nullity of M at P, and the codimension of these spaces is called the coindex of nullity of M. This distribution were studied in the middle 90s, in 1952, was introduced by Chen and Kuiper, and then studied by Maltz and other mathematicians in that period, and they appear naturally in many problems. But the problem when you work with an arbitrary Riemannian manifold is, of course, that these spaces may not all have the same dimension, and therefore they do not define a distribution in the whole M. Because if you change the point, you can change the dimension of the nullity space. However, well, if this is what I just said, the index of unity may not be constant, but you can always take a subset of M, which is given by the points where the dimension of the index of nullity is locally constant. So you can prove that the constant is, of course, always the same. And this is always an open and dense subset of M. And in this open and dense subset, you have a well-defined distribution, which to every point of the manifold assigns the nullity space at that point. This distribution is always autoparallel, which means that if you take the derivative with respect to the Levi-Civita connection of one vector which lies in the nullity in the direction of another vector which lies in the nullity, you always remain in the nullity. The difference with parallel distributions is that one distribution is parallel if you take the derivative of something which lies in the distribution in any direction, and you always and the result belongs to the distribution. And this in general implies by the Riemann decomposition theorem that you can split off one factor. When you have an autoparallel distribution, you don't have this, luckily, otherwise there would be nothing to study. But this immediately implies that the distribution is integrable, and the ellipses of this distribution are totally geodesics, and since they are given by the nullity of the curvature tensor, they are flat. We will then denote them by n of p. So to summarize, you take any Riemannian manifold, and in an open and then subset of this manifold, you can assign to each point the subspace which is of vectors which annihilate the curvature tensor. You can think, if you want to imagine something which is trivial actually, you can think of a cylinder, and the nullity, the ellipses of nullity are the flat lines, and then you have well, that your manifold is foliated. In this case, it is a product, so the nullity is one of the factors actually of your manifold. Since it is given by the nullity of a geometric tensor, which is a curvature tensor, which is invariant by isometries, you have that the nullity distribution is a distribution which is invariant by the group of isometries, which means that if you take any isometry of M, then you will map the nullity subspace at P to the nullity subspace of F at P by the differential of F, or you will map the leaf of the nullity of R at P to the leaf of the nullity of R at F of P. We are interested in studying the nullity distribution and other geometric distributions in homogeneous spaces. Of course, when you have a homogeneous space, you will have that you can reach any point from any other point by an isometry, and this already implies that if you have a homogeneous space, then the index of nullity is constant on M, and therefore you have a well-defined invariant global distribution on M, which is what we call the nullity distribution of the homogeneous space. I will make some remarks on the group G and the group G tilde. The group G is a presentation group of your homogeneous space, which we consider as a subgroup of the full isometry group, but it may be different. I mean, you know that G is a group of isometries, but maybe your homogeneous space is presented by a group which is not the whole group of isometries. Maybe you don't know the whole group of isometries. And this is important because we will try to relate, as I will say later, the existence or non-existence of unity with properties of the group G, or easily algebra, or the whole isometry group. So the first consequences is, as I mentioned, on the case of the cylinder, which is an example one can look at if one gets lost. It's not a significant example at all, but the existence of non-trivial nullity on a homogeneous space without that factor, which is not the case, of course, of the cylinder, impose several obstructions on the geometry of M. Why do we always ask that to work with not necessarily reducible homogeneous spaces, but just without a flat Riemann factor? Because you can always construct homogeneous spaces or any manifold with nullity, the nullity as big as you want. If you make the product of n times anything you want, you can guarantee that your manifold will have nullity, because you are making a product with the Riemannian product with a flat manifold. But of course, these examples are not interested. So we wanted to study or to know whether is it possible to find homogeneous spaces which have no trivial nullity and which have no Euclidean Riemann factor? Why one might want to look at these things? Because what happens in the most beautiful homogeneous spaces, which are symmetric spaces, is that this is not possible. If you have nullity in a simply connected symmetric space, this nullity must be the flat Riemann factor of the symmetric space, and the other factors of compact or non-compact time won't have nullity. So a natural question is, okay, what happens when you instead of working with symmetric spaces which have a lot of abstractions, think of homogeneous spaces?
Francisco,
Sí.
Francisco,
Sí.
a question. If you have non-trivial nullity, does that imply something on the Ricci curvature? You have nullity for Ricci, or?
Yes, I think so. We have you have no nullity. Yeah, I will show you in I think I put it here. You always can construct something which is in the nullity of the Ricci tensor, if I don't remember bad.
Okay, thanks.
I think.
Thanks.
If I don't get there soon, recall me. So, well, what happens? The first is a result, which is a technical result. But, okay. I'm sorry, I left the presentation and I don't know where it is now. Here, okay. So, one of the things that geometrically happen in homogeneous spaces is that if they have nullity and they don't have Euclidean Riemann factor, then and the group is, we assume that is the whole connected component of the isometry group. Each integral submanifold is a closed embedded submanifold and is homogeneous, and the quotient is a differentiable manifold. But the nullity foliation is not a homogeneous foliation. What does it mean? That you have your manifold will be foliated by the homogeneous flat submanifolds, but there is not a group which leaves all of them invariant. Each of them have a different representation group. The interesting thing of these constructions, which is a first abstraction, you have to have a homogeneous space which is foliated by flat spaces, is that you can define an affine fiber bundle which with standard fiber, which is isometric to Rk, where K is the index of nullity, which means that you will have that the fibers of the bundle are actually the leaves of the nullity, and the perpendicular distribution to the nullity defines an affine connection on this bundle. Well, the interesting thing is that the connection will have transitive holonomy. What is the holonomy in this case? You are taking a fiber bundle where the base manifold is a projection of your manifold to the quotient space of M by the ellipse of the nullity. Therefore, the fibers, as I said, the vertical spaces will be the leaf of nullity. And the fact that the perpendicular distribution to the nullity defines a connection means that you can go, the parallel transport for a connection defined this way is like to go horizontally, which means that you can always go, the fact that the holonomy is transitive means that you can join n2 points of your manifold M, your homogeneous manifold M, with a curve which is always perpendicular to the nullity. Therefore, you can move always on your manifold, avoiding the nullity points that the tangent space is never in the nullity of the curvature tensor. So the first question, as I said in the beginning, is if there are homogeneous spaces with non-trivial nullity, which we already know they are, but that was the first question we thought of. And the point is that why do we ask this? I already said this. If you have a simply connected symmetric space, the existence of nullity implies that M has an Euclidean rank factor. So if M is of the compact or the non-compact type, of course, the nullity must be trivial. In a homogeneous space, one has that if you have a simply connected Riemannian homogeneous space without flat rank factor, the fact that the representation group is compact implies that the homogeneous space cannot have nullity. And at the level of Lie algebra, you have a more general result, which says that if the Lie algebra of the representation group G is reductive, in particular if it is compact, then the nullity must be trivial. So, in order to construct examples of homogeneous spaces with non-trivial nullity, the main problem could be stated in this way. We would like to find abstractions that existence of non-trivial nullity imposed to the representation group G or the full isometry group G tilde, for instance, that says, okay, if it has non-trivial nullity, the group G must be solvable, which happens in some cases, or something like that, or abstractions on the Lie algebras or G of G and G tilde. So in order to obtain these abstractions and to be able to construct examples, what we do is to study some important geometric distributions on M, which are the osculating distributions and the distribution of symmetry. So the main tool to study these things is to study geometric distributions which are defined by Killing fields. I don't know if the importance, but the interesting thing about studying these things through Killing fields is that you can actually imitate somehow what you do when you study or you describe the subspaces of a Lie algebra of a symmetric space, and instead of working with the Lie algebra at the level of Lie algebra, of left invariant vector fields or right invariant vector fields, you work with Killing fields, which also defines the Lie algebra of the isometry group in the following sense.
Fran?
Okay. See. Yes.
One question. Sorry. Do you think about the metrics? I mean, can you have different metrics on the same homogeneous space? Because here you ask for conditions on the group and on the Lie algebra. What about the metrics? Do you know?
No, conditions on the group and the Lie algebra, but there are examples, there's a family of metrics on the same. I should look. This was on the paper of 22, and I should revise exactly which example is. But I think that we could construct examples of, for example, a given homogeneous space which has always nullity of dimension 1 for a family of homothetic actually metrics, different metrics. But we didn't think of the metric. For us, the homogeneous space is given with a given metric. I don't know if I answered your question. If you could have different metrics on a homogeneous space with nullity, the answer is yes. If we thought of conditions on the metric for the nullity of to exist, no.
No, I'm thinking if you. Yeah. But okay, I will wait for the end. Don't worry. But yeah, okay. Partially, thank you.
Ok, otra vez perdí la presentación. Here, sorry. So, in this first part, I will introduce these distributions and I will recall some basic facts about Killing fields in order to work with them and to be able to define the distributions and that they are more in a more comprehensive way. So we start with a homogeneous space M, which is given by a group of isometry G, and you can consider the Lie algebra of all Killing vector fields of M, which means that you have a vector field whose flow is by isometries, or such that an equivalent condition is that you have a skew-symmetric transformation of the tangent space at each p, where nabla for us will be always the Levi-Civita connection. And you can identify, as usual, the set of all Killing vector fields with the Lie algebra of the whole isometry group by assigning to each element of the algebra the Killing field which defines the exponential. So since we wanted to work with the presentation, any given presentation group G, meaning that you don't necessarily have the whole isometry group, one always or frequently have to consider Killing vector fields which are induced by the presentation group. What does it mean? You take Killing fields whose flow belongs to our isometries that are in G. In this case, you can identify the Lie algebra of G with the Killing fields which are induced by G. Okay. So other than satisfying what we call the Killing equation, which means that you have a skew-symmetric transformation of the tangent space at every point when you do nabla of X, the Killing vector fields satisfy the affine Killing equation. If you take if you consider that isometries are particular cases of affine transformations, which are transformations which only preserve the Levi-Civita connection, then you will have that if you have a field whose flow is an affine transformation for the Levi-Civita connection, you will have an affine Killing vector field. So in particular, Killing vector fields are particular cases of affine Killing vector fields, and the condition of a vector field for B an affine Killing vector fields is a condition on the second derivative and the curvature tensor. I mean, a vector field X is an affine Killing vector field if it satisfies this equation here. And since Killing fields are affine Killing vector fields, they verify this equation. So why one wants to study or one wants to think Killing fields are affine Killing vector fields? Because Carlos and Sergio Console defined a connection which is actually a constant connection based on a previous words of constant on a particular fiber bundle, which is the following. You know that a Killing field is completely determined by its initial conditions, which are its value at the point and the value of this operator, nabla X, at that point. So any Killing vector field is determined by one element on the tangent space and one element here. Therefore, you can think of this fiber bundle, which reunites all possible eventual initial conditions. I mean, it doesn't mean that if you fix a vector field, a tangent vector and a skew-symmetric operator, you will always have a Killing field with those conditions, of course. But all the initial conditions of Killing fields are on this bundle. And you can define a connection on this bundle, which is given this way. If you look at the first thing, you are asking that the operator nabla of zeta coincides with the operator B that you choose here. And if you look at this, you will realize that you have, since B for you will be nabla of X, if X is a Killing vector field, you will have the affine Killing equation. So what they got is that, okay, I already said this, you have a Killing field, which is determined by these conditions, and constant connections, what we do is to allow to consider Killing vector fields as parallel sections of this connection on this vector bundle. So you have that XB is a parallel section of the vector bundle E, the fiber bundle B, if and only if X is a Killing field of M and B is nabla of X. So in particular, why is it useful for? Because we said that what we have here is that you, in order to know a Killing field, you only need to know its initial conditions at a point P. But in many problems, you want to obtain the initial conditions of the Killing vector field X in a point Q, but you don't know the Killing field. You only know that the conditions that it satisfies at another point P. So what the constant connection allows you to do is to reobtain all the initial conditions, which are the values actually of the Killing field at any point by parallel translating or transporting the initial conditions of X at P along any cube that joins P with your point with respect to this connection. So another thing that was fundamental and which is useful when working with Killing fields is the following. We said that our main purpose is to identify any Killing vector fields to its initial conditions at a point P. And we wanted to, instead of working with the usual method of the algebras or of taking the bracket, not the bracket of considering left invariant vector fields, you want to consider Killing fields, which define the algebra of the isometry group. But the problem is that if you take the bracket of two Killing vector fields, you will obtain, of course, another Killing vector fields, but it's important to know which are the initial conditions of the bracket on the same point P, but you want to express the condition of the bracket X and X prime, for instance, if you have X and X primes two Killing vector fields, with respect to the initial conditions of X and X prime. So as a consequence of the Killing equation, the affine Killing equation, you obtain that the initial conditions of the Lie bracket are given this way. So in particular, why this is important? Because you can use that the Lie bracket, the symmetry of the Levi-Civita connection, to obtain the curvature tensor in terms of Killing vector fields. So you will have that the curvature tensor evaluated in two vector fields of a homogeneous space, Killing vector fields of a homogeneous space as a point, are given by this. And you can rewrite the Koszul formula for Riemannian manifolds in terms of Killing fields, and you get a quite nice formula, which is this one. So we know how to work with all the geometry of a homogeneous space when we want to consider the algebra of the full isometry group considered as the algebra of Killing fields of the homogeneous space. You can compute everything on the geometry of the manifold. So related to this, or a first distribution which appears, is the distribution of symmetry. If you think of a symmetric space, when you study the Cartan decomposition P plus K, you have the Lie algebra of the isotropy group, and then you have a complement which is given by transvections. What are transvections? Well, transvections are given by Killing fields which are parallel at the point, which means that if you have a point P of M, then a Killing vector field is called a transvection at P if its initial condition are some vector, which of course will be X evaluated at P, and 0. This means that the operator nabla of X at P is null. So you can think in any Riemannian manifold, you can define the space of symmetry at a point P, which is you take all the transvections at P, the transvection is always at a point, and evaluate it at this point, and you will have a subspace of the tangent space. These subspaces which have a dimension, which is called the index of symmetry of the manifold at P. The codimension of these spaces is called the co-index of symmetry at P. And again, this is a geometric distribution. Therefore, if you are working with a homogeneous space, I'm sorry, these are geometric subjects, and the problem you always have with these subjects is that the dimension could vary from point to point, and therefore you won't have a distribution defined in your whole manifold. But if you are working with a homogeneous space, the index is of symmetry is constant, and you have a well-defined distribution, which is called the distribution of symmetry. And the common value is called, of the index of symmetry at every point, is called the index of symmetry of your manifold. The distribution of symmetry is autoparallel. There is a pa missing. And it is integrable with totally geodesic integral manifolds, which are called the ellipse of symmetry of M. It was introduced by Carlos, Olmo, Silvio, Bernd, I think Tamaru. And in these two papers, which I will show at the end in the bibliography, they prove that if you have the distribution of symmetry, which somehow measures how far your homogeneous space is from being symmetric, then the ellipse of the symmetry are always globally symmetric spaces. You will have that if M, you have a simply connected space, then M is symmetric if and only if the symmetry is everything. You have transvection in every direction. Here I am always assuming that you have a homogeneous space. And if M is not locally symmetric, then the coindex of nullity, the coindex of symmetry is at least 2. Since we will be working always with simply connected spaces, sorry, I couldn't think of the word. Simply connected spaces, you will have that in a simply connected homogeneous space without flat factor. If it cannot be locally symmetric, otherwise it would be symmetric and it would split off an Euclidean factor, then the 2 is the least possible index of symmetry for your space. And what is the relationship with nullity? Well, actually, this was one of the biggest problems, which was to prove that you always have transvections in the direction of the nullity. But this means that if you have a simply connected Riemannian homogeneous space with no trivial nullity and which does not split off an Euclidean factor, this will be always the hypothesis, so I won't read it each time. Then the nullity distribution is contained and not equal to the symmetry distribution. So you have to have conullity at least 3. So if you have a homogeneous space which has a non-trivial nullity distribution, which will always means that you don't have an Euclidean flat factor, then you have a bound for the conullity, a lower bound for the conullity, which is 3. And this will be one of the keys to find examples of manifolds, because at this point we don't have any. So what other things are important on, what time is it? I'm quite behind. But what other distribution or what other problems are important is that one is called the osculating distribution, which you can define for any distribution on any manifold. So, well, sorry, not on any manifold, on any homogeneous space. So if you have a homogeneous space M and you have any homogeneous, any distribution which is G invariant, then you can define the first osculating distribution, which is you take your distribution and you sum up the span of all the derivatives of the section of your distribution. If you think so a little bit about this, the first osculating distribution in some way tells you how far, or not how far, but why your distribution could not be parallel. I mean, if you have a parallel distribution, which will makes you split a factor, you will have that this part of the osculating distribution already lies in D. So here you could have things which are in D, but somehow you add all the possible derivatives, and the oscillation distribution, of course, has sense as long as D is not parallel, otherwise they would coincide. And an interesting thing is that
excuse me, why do you need G invariant? Can't you do it if the distribution is not invariant?
Well, I think you could. Actually, the definition, yes, you don't need it to be invariant. You can define each subspace. I'm not sure if you will find, there may be some problems with the dimension if it is not invariant. I mean, you have a distribution, you take all the derivatives, and I imagine that you could modify the dimension at different points and not to get a distribution. Okay?
I see.
I'm not sure. I mean, we wanted to work with the nullity, and we defined it for general G-invariant distribution, but I think you can guarantee that it is a distribution because it is G-invariant. Otherwise, you should prove something else. And we wanted to have, again, G-invariant distributions. That's why you start with the G-invariant distribution. So the first osculating distribution is G-invariant and contains, of course, the distribution, the origin distribution. What I already said, if your distribution is not parallel, your original distribution is properly contained on the distribution. And the interesting thing is that this is quite difficult to obtain, actually. Not quite difficult, but it gives you it may be quite difficult to obtain, but you can always think of this as your original distribution by plus an other distribution, which is called the adaptive distribution, which what does is that you can consider in a homogeneous space only you have to consider the derivatives of Killing fields which are induced by your group, your presentation group, in the direction of things that lie in your original distribution. So you have two different things to describe this first osculating distribution. This is more geometric, and this is like the more important part when we study the nullity things. So if you consider D as the nullity distribution, you can obtain the first osculating distribution, which is nu q plus nu hat, which is this, the same I already said. But you have again a G-invariant distribution, which is nu1, and then you can consider the osculating distribution to nu1, which is called the second osculating distribution. The interesting thing is that if you think of this part, I will go back. This description is more useful to us, but it depends on the presentation group and the distribution D. What depends on G is its G invariance. But for instance, if you have the nullity, since the nullity is invariant by the full isometry group, it will be invariant by any presentation group you have on your space. And these adaptive distributions, which are the ones which have the hat, of course, depend on G, because you are always only taking Killing fields which lie in G, but the osculating distributions don't. They are well defined on your manifold as a homogeneous manifold. So with this introduction, what we have here are the ingredients. You have a homogeneous space. You want to know if your homogeneous space can have nullity or not. And you start to study some distributions which are associated, geometric distributions, which will be associated with the nullity, which are the osculating distributions and the symmetry distributions. As I already mentioned, the existence of nullity implies the existence of symmetry, which already imposes a condition for the existence, for the nullity to exist. And one of the interesting things, because we actually didn't know, if you look at this, if you could have, well, it doesn't matter, here. I put it here to 2022 and 2023 because we knew that there would be, if your manifold had nullity, it should have not trivial symmetry, and there are always, we knew that there were always transvections in the symmetry distribution which are not in the nullity distribution, but we actually didn't know if any vector tangent to the nullity would be the initial condition of a transvection of your homogeneous space, which means that we didn't know if the nullity was included in the symmetry distribution on the first paper we published. So at this point, we wanted to relate the nullity with these osculating distributions, which are always not, one is included and not equal to the other, if you assume that you cannot split a fact factor, otherwise they could coincide because the nullity could be parallel. But this gives you that something that we knew is that the connullity of M, we know, we didn't know, we knew it later, that the connullity of M is at least 3. And you can obtain this using this relationship, which means that you have 3 distributions which are concatenated and are all included in the other and different from the other. Therefore, you have to have connullity at least 3. Or you can use that the nullity is contained in the symmetry distribution. The symmetry distribution must have at least connullity co-index of symmetry 2, which was proved by Silvio, Carlos, and Jürgen. And therefore, the nullity distribution, which cannot coincide with the symmetry distribution, you should have at least connullity 3. It says it is the least possible. And the other thing which was interesting before we could prove that you can actually find a transvection in the nullity is that you can always find a transvection whose initial condition lays at least here. And this implies that you have a vector here which have a Jacobi operator which is always 0, and that in this direction, and that with the transvection whose initial condition is V, for any V you take in nu hat, which will be non-trivial, otherwise nu would be parallel. For, I said, for any initial condition you choose, you can find a transvections which satisfy this equation. It's different from 0. No, it's 0, I'm sorry, but E with Km should be non-zero. So as the point is that this is, again, these initial conditions can be again stated as brackets of other Killing fields. So one of the consequences of this result is that you get another of fractions, that is that you will always have a trivial nullity when the algebra of your presentation group is two-step nilpotent. So at this point, we didn't have any example. We knew that in compact cases, reductive Lie algebras or two-step nilpotent Lie algebras, we wouldn't find nullity, and that the nullity should have the nullity distribution should have codimension 3. Another result, which is structural, was that I'm running out of time, so I will skip this, but the interesting thing is that if you have a simply connected Riemannian manifold without a Euclidean factor, and you have connullity, you have nullity, and therefore you have connullity, then your isotropy group should be isomorphic to SO K less 2. So in the particular of the less possible nullity, which is connullity, sorry, which is 3, you will have to have a trivial isotropy group, which means that you will have to have a Lie group. And in addition, this Lie group should be solvable. So the problems at this point is, of course, to find the example of homogeneous spaces with connulity 3, and if the condition of the isotropy to be trivial and the group to be solvable were actually necessary conditions. If this any homogeneous space with non-trivial nullity should be a solvable Lie group. Well, we could actually answer the first one and parts of the second one, and that is the last part, which I will go a little bit quicker. Then, if you want, you can look at this. The point is that with all these things that we have here, with the results of the distributions, with the existence of transvections, and the existence of different restrictions on the Lie algebra G, you can actually imagine what an example would be. And actually, you propose a group of matrices, which is a semi-direct product. We use a computer and one compute things. You can define an explicit example in any dimension with connulity 3, which is a simply connected Lie group, solvable, whose metric, you have a left invariant metric, and you know that you can explicitly define which are the vectors which lie in the nullity, which are all but 3 of a given basis, which you construct this way, and therefore we constructed examples. Actually, there are examples of irreducible homogeneous spaces with that actually Lie groups, solvable Lie groups with the left invariant metrics, which have connulity 3. So the final results and open questions are the open questions that we already had. We could find examples with connulity 3. They should be solvable Lie groups. But what happens if you have a connulity bigger or equal than 4? Sorry, here you should put an equally. And are there examples with non-solvable groups or non-trivial isotropy? At this point, we didn't know either if we could have transvections in any direction of the nullity. And well, this was part of the last work which appeared last year, and you generate new geometric distributions. In particular, what is important here is that you can always take the transvections. First of all, that finally one can prove that any vector of the nullity is the initial condition of a transvection, and therefore you can consider the Lie algebra, which is the vector space of transvection at P, whose initial condition is in the nullity, and these generates an abelian ideal of the Lie algebra of the full isometry group. And with this construction, one can actually give an explicit construction in any dimension of, again, a Lie group with a left invariant metric, which has connulity as big as you want, or nullity as big as you want, but it's not solvable. The group is not solvable, and moreover, it never admits the action of a transitive group, of solvable transitive group of isometries. From these examples, you can all have that you can take compact quotients, which are locally homogeneous. So, and they have non-trivial nullity. Therefore, as we said, any compact homogeneous space with trivial nullity should have trivial nullity. Therefore, you cannot eliminate the homogeneous. You won't find a similar result for local homogeneity. And the open problem is still to find examples with non-trivial isotropy. And okay, we are currently working, just to mention, we are currently working with Ryan and Silvio about how to generalize these things to Lorentzian spaces. of course, when you work with Lorentzian spaces, you have the problem of degeneracy. All the distributions that appear here are not necessarily non-degenerate. The first results we obtained, or the most recent developments, are to obtain the symmetry distribution for a particular case, which is which are naturally reductive nilpotent Lorentzian groups, whose behavior is analogous with the Riemannian case, and more results hopefully will come soon. So here are the papers that I mentioned, and thank you all for your attention.
Okay. Thank you very much, Francisco, for your very nice talk. Okay. And now we have some minutes for questions, comments. Is there any?
Francisco?
I don't know. I was
No, but
thinking.
I mean, since in the homogeneous case, Ricci flat implies flat.
Yeah.
I've seen that many of your results are actually valid for Ricci nullity.
For Ricci.
Okay, which is much simpler. So my question is about what is known about all this, the same story, but with Ricci nullity.
Yeah.
What is known about Ricci nullity? If I wanna do,
I don't know. I actually don't know. Yeah, we use this fact that if you have this for the examples, but I don't know.
Okay, because it's like most of your results on Lie groups, solvable, nilpotent, is I've been checking, and
yeah, actually we use what you are mentioning with the proof of the fact that it cannot be two-step nilpotent, for instance, is actually was a consequence of the construction, but it's actually well known, and it follows from the fact that if you have a two-step nilpotent, it has to be Ricci flat. So
yeah, and also
about the maybe Carlos knows
examples is like you are also like constructing almost abelian with the with the kernel for Ricci, with a lot of kernel for Ricci. That's why. But okay, yeah, it's
thanks.
Okay, thanks.
Okay, are there any other questions for Francisco?
Vivi?
No, just I see now that it was a different problem that you were working with, and you got these examples. But what I was thinking is, in the same examples that you have, can you have metric? I mean, you have metrics which have nullity. Can you have metrics in the same Lie group that
without nullity,
for instance? Yeah, this was that.
I don't know, because I would say no, but because, well, you are taking there, I mean, I don't know, we should think of which are the hypotheses, but because if you are considering that your Lie group, your presentation group, is also a group of isometry for your new metric, for instance. Otherwise, you should change the presentation group and you change everything, and yes, the answer would be yes. But you know what I mean?
Yes.
You have a metric which is invariant by the same group, but it's a different metric. Then I think you should, if you have nullity in one, you should have nullity in the other one, because of the. But I don't know. I'm not sure of what I'm saying. But the constructions are geometrical and depends on the algebra structure, and therefore you should get things on the nullity if you change the metric. But you have yeah. But can you? It's an interesting question.
I don't know. Don't worry. I see that the problem was already to build examples was a huge challenge. So This is what, just to clarify what was the question. I don't know.
Okay.
And one small thing, the definition of the nullity and so on, does it depend on the metric being complete, or you can, any metric? Later you go to homogeneous, but you can define on any Riemannian manifold.
Yeah, but you won't have
nullity.
You can define unity of anything you want. I mean, you have an operator, and you will, and
Sure.
in general, if the operation behaves well enough, you will have an open-ended subset where the nullity is well defined. Actually, for example, if you work with some manifold geometry of, well, in fact, of space forms, you can define the nullity of the shape operator, and you have the same results. There's always an open-ended subset. This geometric nullity distribution of different tensors were studied by Maltz, and in these papers, which are here, they are different. But no, you don't need it to be complete. Of course, if you want to have interesting results of the geometry, you probably have to add hypotheses, because when you study the nullity, one of the common denominators of the problem with nullity this would be the intrinsic case, which you study the nullity of the curvature operator. But for example, if you work with some manifolds and you want to study the nullity of the shape operator or other geometric operators, is what happens when you don't have a product. So you always have the hypothesis that you have or irreducibility, or for examples, I remember when I worked with some manifolds and the nullity of the shape operator, you should add completeness in order to have global results. Otherwise, you always get like local results or things like that.
Okay.
Francisco, hi Francisco.
Yeah. Hi Paolo.
I have a quick question. Maybe you have already commented this along the talk. I'm sorry I entered late. What is the maximum value of the nullity and co-nullity? Dimension of the manifold, or dimension of the manifold minus 1?
Dimension of the manifold minus 2 of the symmetry and minus 3 of the nullity. I mean, if you have always that you have. This is interesting to say the bound between the nullity and the index of symmetry. You have, for example, if you have the index of symmetry, which is n, the full dimension of the manifold, you have to have a symmetric space. But if you don't have a locally symmetric space,
if and only if, right? If and only if.
Yeah, it's an if and only if you add simply connectedness. Otherwise, you could have a locally symmetric space. But if you go to homogeneous spaces, which are no locally symmetric, then the index of nullity, the co-index of nullity is 2. That's the less possible value. And the nullity lives always in and it's not equal to the distribution of symmetry, so you have to have co-index 3. That's the minimum possible. And then in the example we constructed, you can have the dimension you want and the co-dimension you want, actually, but greater than 3.
Okay, I see it.
Actually, if you study the CN2 manifolds, which we were looking at that, you cannot have CN2, you can have manifolds with conullity 2, which are the CN2 manifolds, but they cannot be simply connected homogeneous spaces, because they would be locally symmetric and then
yes. And in the symmetric case, can you tell the rank with this theory, like
the rank of
the symmetric space?
If you know the index of nullity.
Well, the index has to be maximum, right?
Yeah, of course.
There must be something else.
I don't know with which information, because the nullity doesn't tells you anything in a symmetric space. You just split off an Euclidean factor.
Okay.
So nothing of what I did here has sense in a symmetric space. Okay. Because as you say, you have maximal index of symmetry, and if you have nullity, you take it apart. And I actually don't know. I'm sure Silvio or Carlos, which have worked in these things, know better than me. But I don't see how you could get the index of the space from these elements, because you cannot use them in a symmetric space.
Thank you. Sorry. Yeah.
Okay. Well, are there any other questions for Francisco?
I have one little question.
Yeah.
In the last slide, you mentioned something about a naturally reductive nilpotent.
Yes. Yes.
And Lorentz metric,
Yes.
right? Well, in the Lorentz case, is it known if there is? I mean, does it have to be two-step or?
Yes, it's I think yes. I don't remember exactly, but when we started studying the problem, we didn't know it. It's not that was one of the big problems with the Riemannian case, which you know that it has to be.
Yes.
But there is a paper of I don't remember the name. I should look at in the references. An Australian guy. But yeah, it was proved like last year that it has to be two-step, with some condition, of course, of non-degeneracy of the center and things like that. But yes, I think that in the most interesting cases, it has to be two-step nilpotent.
And is it for the Lorentz case or an arbitrary semi?
No, you have to, well, you could start, no, I mean, no, with arbitrary signature, I think. I'm not completely sure, I should check, but there are some recent works which tells you when it has to be two-step nilpotent. In Lorentzian case, I'm quite sure. I'm not sure in the primary case. What we did is for Lorentzian case, because you needed to be Lorentzian in order to decompose some things. Otherwise, you have a lot of degeneracy which you cannot control.
Okay.
Of course, it could be nice to.
Thanks.
You're welcome.
Okay. Well, are there any more questions? Okay, if not, okay, let's thank the speaker again. Thank you, Francisco.
You're welcome.
Very nice.